Welcome back to another exam walkthrough. We're going to be going through 2024 October, question 4, 5, 15, and 17. So you can pause the video, you can go through the questions yourself, and then watch me do it. For the MS and ER, you can go to the end of the video. Okay, question number 4 says the photograph shows a cable car hanging from a cable. The cable car is in equilibrium. That means that the resultant force is equal to 0. And it says which of the following forms in Newton's third law pair of forces with the weight of the cable car. Now, the cable car is experiencing a force of a gravitational force that is exerted by the earth on the cable car. So it's going to be force by earth on cable car. Okay. Now, the cable car also must exert a gravitational force on the earth. So this is going to be the gravitational force by the cable car on the earth. Right? And we should note something very important, that for Newton's third law pair forces, they gotta be the same type. Weight is a gravitational force, which means its pair, its Newton third law pair, must also be gravitational force. And if the force is on the cable car by the earth, then the other one should be by the cable car on the earth. Okay, let me just write that down as well. So you can notice here the gravitational force on earth by the cable car, the gravitational force on cable car by earth. Okay, so the answer here, I think it's quite obvious, it's going to be B. Question number 5 says a box slides down a slope at a constant speed. That means that the forces must be equal. The resultant force must be equal to 0. Weight and resistive forces both act on the box. Which of the following is the reason why the speed of the box is constant? So I can see a lot of options, and I can see a lot of equals to here. And then I can see greater than. Now the greater than ones will probably be wrong. And the equal to ones, it's either going to be A or C, right? Because your speed is constant, your resultant force should be equal to 0. Now, a box going down a slope is basically a box going down an inclined plane. So it's going to be something like this. Now we've got the weight acting, we've got the frictional force, we've got the normal contact, and this angle is theta. So this is going to be 90. This should be 90 minus theta. And this angle right over here is going to be 90 minus theta plus x, let's call this angle x here, is equals to 90. So we'll get x is equals to theta. So this angle over here, which we said was x, is actually just theta in disguise. So we're going to do the same thing again. We're going to have the weight, we're going to have the resistive force, we're going to have the normal contact, and we're going to have this angle as theta. So we're going to make two components of the weight now. So this is going to be, this component right over is going to be w cos theta, this is going to be w sin theta. Now, since the object is traveling at constant speed, it should be in equilibrium and all the forces must balance out. So w sin theta is equals to the frictional force, or the resistive force, and then the normal contact should be equal to the w cos theta component. Okay, now we'll read this carefully. The component of weight perpendicular, or actually we shouldn't be reading this one, let's read the C one. The component of weight perpendicular to the slope is equal to the sum of the resistive forces. We can see that the component that's perpendicular, w cos theta, is equal to the normal contact, not the sum of the resistive forces. So this is going to be wrong. The component of the weight parallel, which means w sin theta, is parallel to the slope. This is perpendicular, this is parallel. So the parallel component is equal to the sum of the resistive forces, and we can see that's true. So the answer is going to be A. I hope that's clear. Question number 9 says two boats A and B are pulling a ship. Each boat is attached to the ship by a rope as shown. The force from boat A on the ship is Fa. The force from boat B is Fb. Which of the following expressions gives the forward component of the total force of the boats on the ship. So we're going to find the forward direction or the x direction. So we just have to make components here. So this component, this component, this and this. This is going to be FA sine 31. This is going to be FB sine 27. This is going to be FB cos 27. This is going to be FA cos 31. When you add both of these, you get the forward direction force. Okay, combine both of them, you get the total force. So that's going to be C. Okay, so question number 15 says, in a high jump competition, athletes jump over a bar. An athlete has a weight of 680 newtons. The athlete exerts a force of 890 newtons on the ground as he jumps into the air. Explain why the athlete accelerates upwards. The answer should refer to Newton's third law. Okay, so what's going to happen here in a nutshell is that the athlete will exert a force of 890 newton on the ground. And by Newton's third law, the ground will exert a force of 890 newtons on the athlete. Okay, so we're going to have those forces. They're going to be equal in magnitude, opposite in directions, acting on different bodies. They're going to be the same type of force. Okay, now I'm going to draw the free body diagram of the athlete just before he's about to jump and, go in the air and accelerate upwards. So we're going to have that 890 newtons force, and then we're going to have the 680 newton weight force. So these are the two forces that are going to be acting on the athlete. This is going to be the force from the ground, and this is going to be the force from the earth. So we can say that 890 newtons minus 680 newtons, there's going to be a resultant force equals to MA, right? So 210 newtons is going to be the resultant force equals to MA, and hence the athlete will accelerate upwards. Okay, so by Newton's third law, ground exerts a force of 890 newtons on the athlete, equal in magnitude and opposite in direction. The upward force is greater than the weight, so by Newton's second law, the resultant force is upward. And basically, you can write that there is a resultant force that's equals to MA, right? And 890 newtons minus 680 newtons, the resultant force is 210 newtons. So you can even calculate the acceleration here. So 210 is equals to MA. So 210 is equals to 680 is the weight. So 680 divided by 9.81 is going to be the mass, and you can calculate the acceleration from this. So the acceleration is going to be 3.03 meter per second square. So that's going to be the acceleration. Alright, that's all for question 15. Now let's move on to the 6 marker, question 17. Okay, now we're going to be doing question 17. It says a student is about to do a bungee jump from a high bridge. The student is attached to the bridge by an elastic rope. The student jumps from the bridge and initially accelerates. The diagrams show the student at 3 different positions during the bungee jump. At position A, the distance fallen by the student is equal to the original length of the rope. At position B, the student is in equilibrium. And at position C, the rope has maximum extension. So part A, the 6-mark question, explain how the acceleration of the student changes as she moves from position A to position C. Assume the air resistance is negligible. Alright, so I'm going to take a different page and I'm going to try to explain this question. So let's do that. Alright, let's try to understand this question now. So we've got position A, B, and C. Now just for context, I'm just going to tell you one more position. Let's call it position 0. Okay, so the person is going to fall from here, and the resultant force is equals to MA. Now when he initially falls, the weight will be the resultant force. So mg is equals to MA. Okay, now after the wire becomes taut, which means it becomes its original length, the rope, okay, not the wire, the rope, so the rope will become taut. That's when you will have the tension coming into the picture. So now we're going to have the tension, and it's going to be less than the weight. Okay, so the acceleration will be downward. Alright, the acceleration will be downward. Now, as the rope extends, as there's extension, the tension will increase in the rope. And then at position B, the tension will be equals to the weight. Okay, So as the tension is going up, what's going to be happening is that the acceleration will be decreasing in magnitude. Okay, the acceleration will be decreasing. And because of this, also remember the resultant force is also going to go down. Alright, until the tension is equals to the weight. Okay, so that's going to be when we have the acceleration as 0 and the resultant force as 0. Remember always to link resultant force and acceleration together. They go hand in hand, right? And then from position B to position C, what's going to happen is that the tension is now going to be greater than the weight because the rope will further extend, and the resultant force is now going to be upwards, and the acceleration will also now be upwards. Alright, so I hope that's clear. That's all you got to talk about. The resultant force, the acceleration, the forces. Okay, so I hope that's clear. Now we're going to write down the answer. So this is going to be your answer. After A, tension acts on the person. Tension is less than the weight, so the acceleration is downwards as the resultant force is downwards. So the equation here is going to be weight minus tension is equals to MA. And then as the rope extends further, the tension increases, so the acceleration downward decreases as the resultant force decreases. Okay, now at B, tension will be equal to the weight, so the resultant force is equal to 0 and the acceleration is also equal to 0. Make sure you write down the resultant force is equal to 0 and acceleration. I've kind of been a bit lazy here and written down the symbols instead of words, so make sure you write it in words. It's just better. Okay, then after B, your tension will be greater than the weight, so the resultant force will be upwards and acceleration is also going to be upwards. So it's going to be now tension minus weight is equals to MA. That's going to be the equation now. Okay, so the acceleration will be upwards now, whereas before it was downwards. Alright, so that's going to be your 6-mark answer.
Would you experience the greatest acceleration? Is it at A, when you immediately leave the platform? B, when the bungee rope is taut? C, at the bottom of your jump when you touch the water? Or D, is it on the rebound? Take a moment now to decide the position. Quick, your time's nearly up. You can see at position A that the displacement and velocity is 0, but the acceleration is at a constant. This is the acceleration due to gravity. There is another point which is greater than this. At position B, we can see the acceleration is still constant and the bungee jumper is nearing his maximum velocity. Soon after, at position C, you can see the acceleration suddenly spike. This changes the direction of the bungee jumper and is the greatest acceleration seen throughout the jump. After this point, the bungee jumper is moving upwards, but the acceleration is slowly decreasing. This changes the velocity once again. This point is not the greatest acceleration. Point C was the correct answer. The misconception here is understanding that the velocity is the speed of the bungee jumper, whereas the acceleration is the rate of change of the velocity.